let's start. Welcome to the next edition of VGS IT. This is the Vision, Graphics and Speech invited talks at FIT, Faculty of Information Technology, here at BUT. And it's my pleasure to welcome Ondřej Dušek from Prague. Ondřej is from the Institute of Formal and Applied Linguistics at the Mathematical and Physical Faculty of Charles University. And as you know, this is the big site for NLP and for machine translation and so on. Ondřej is specializing into dialogue systems and natural language generation. He graduated PhD from Charles University in 2017. Then he was at Heriot-Watt University in Edinburgh, which is actually quite a known place for dialogue systems. And today he will talk about, dialogue systems again. Before I stop my introduction, big thanks to the Student Union of FIT BUT for renting us this place, including excellent technical support. So, Ondřej, the floor is yours, right. And thanks a lot for coming.
Yeah, thanks very much for inviting me. So, hi everyone, I hope you can all hear me. So, today I'd like to talk about basically our recent experiments on dialogue systems with end-to-end neural networks. And first, kind of a disclaimer and also a bit of credits to my students, which basically all of this is mostly their work. I was just there and, just kind of supervising. So mostly Vojta, Jonáš, and Tomáš did like all of these experiments that I'm going to show. So there might be occasions where if you ask me, I won't know and I would have to ask them, but let's see if that happens. So I'll start with like a quick outline of the talk. It's basically divided into 3 parts, 2 of which are kind of like more scientific, the third is more technical. But anyway, so the first one is basically how we implemented like an end-to-end neural dialogue system using the huge pre-trained model GPT-2 with some background on dialogue systems and how to extend that GPT-2 model to work on dialogue. Then I have a second part of the story is kind of a slightly different thing, but you'll see that they are actually connected. And this is actually a way of getting dialogue annotation if you don't have one. So basically all the dialogue systems, especially the end-to-end neural ones, need a lot of data and need a lot of annotation. And if you don't have annotation that somebody did for you manually, I'll show you a way of how to do that using some kind of a generic annotation tools or generic linguistic annotation tools. And the last one is a bit of a look at evaluation. I said it was kind of technical. I'd say the main message of that is that evaluation in NLP and in dialogue is kind of a mess. We tried to clean it up a little bit, but we'll see if that catches on. But it's more of a, what can go wrong when you're evaluating a dialogue system and how to make your numbers actually comparable or your scores comparable to anyone else. So I'll start with the first part, and I'll start with a little bit of background. So in today's dialogue systems research, the trend or the kind of prevailing paradigm is now end-to-end neural systems. Obviously, in commercial systems, you still have this kind of a classical pipeline where you have like language understanding that gets, the user utterance. Oh, okay, maybe this will work better. So language understanding that gets the user utterance and gets some kind of a formal meaning representation of that. Then you have dialogue state tracking, which tracks the user preferences along the whole dialogue. So it's not just the one utterance, one sentence. It's over the whole dialogue. And then you have a database and a dialogue policy that kind of decides what to do next. So in this case, the user said that they want a cheap Chinese place. The tracking kind of got that, but the policy decided that there are too many results in the search and it still needs to know the area, so it decided to request the area. And the final step is a natural language generation, which converts this semantic representation again back to natural language. So that's kind of the traditional way, but the trend now is to represent everything using a neural network. So you have all those components inside a single neural network that typically is trained in like an end-to-end fashion, and the responses are generated basically word by word. So you basically just feed in some kind of starting character, some special token, and then you generate the first word, feed it back in, generate the second word. In this way, I mean, this is like a really simple depiction of all that, but it's basically how that works. The architecture is kind of simpler than it used to be. So basically all those components are integrated except for the database, and that creates a bit of a problems on its own, but the database is, there are actual entries. It's relatively hard to represent them in the neural network, so it's typically kept apart. And most of those systems are text only. So I know that you're strong on speech recognition and these kind of things here, but most of these experiments with the systems are basically text only. So you can kind of imagine that you're texting with the system. I mean, you could probably plug in like an external speech recognition into that, but most of the experiments, or all of those that I'm going to be talking about today, are just text only. So from text with text replies. So this is nice and it's really exciting, but there are still quite a lot of problems. So the first one, it all needs a lot of data. You need a lot of annotated data to train a neural network to do this. And the data is hard to get by and it can be noisy, so there can be some inconsistencies especially in the annotation. Then the second problem is, and that is a problem with a lot of end-to-end neural things, not just in dialogue systems, is that if you kind of fit everything into just one big neural net, it's very hard to control. So you may get cases where the neural network gets the input and the output is kind of inconsistent with the inputs. It doesn't make sense. It's, it can hallucinate stuff like you ask for a Chinese place and it can somehow, based on training data, hallucinate that you actually want the Chinese place in the city center and takes that as your understanding, and you don't know why, and it's hard to actually debug those cases. So that's a huge problem. And the last problem is that even despite having a lot of different sentences in the training data, what you usually get on the output is kind of like the most frequent, most common way of expressing things. So it might get a bit repetitive or slightly dull. So these are like, this is the kind of the current status and the problems. Now let's have a look at the actual task, or how you frame the whole thing with dialogue. So there's a benchmark called MultiWAS that is for task-oriented dialogues in multiple domains. And now what do I mean? It's basically dialogues around hotels, restaurants, attractions, and it's typically just like a user that is a tourist coming into Cambridge and they want to book a hotel, find a restaurant, take a train or something like that. And all those domains are connected. So for example, they are looking for a nice tourist attraction, and then they want to take a taxi to go there and book the taxi. So you have around 10,000 dialogues, so it was, I can imagine how much it costs to actually collect these, which were collected by connecting two real people over the internet. They were both given tasks. One of them was the tourist one of them was like the system or the agent, and they did the whole dialogue. The tourists had some kind of task assigned, like what kind of restaurant they were looking for, or what do they want to do in Cambridge. And then there is a lot of annotation to that. So if you look at it, the user says that they are looking for a train from Cambridge, and the agent or the system has some information from the database, and it's tracking the dialog state. And you have all this annotation included in there. Then the user specifies the date and time. This is all included in the database search. Then the system kind of recommends some kind of a train connection. Then there is a booking, and then the user says, okay, and now I also want a restaurant. And here you can see that actually, the state tracking now includes a restaurant, and it still includes the information about the train. And the database search now involves the restaurant because it's now the active domain. But it's all of it is connected, and there's a lot of annotation, and especially the individual values of so-called dialog slots are annotated, so you actually know that this number is the slot corresponding to the number of search results in the database. This is corresponding to the departure. So this is all annotated, and this all is kind of added to the data. So it's there for the systems to use, and it's actually used very heavily. And one more note: this data set is basically one of the widest used benchmarks in dialog systems, and it also has been used for the dialog systems technology challenge competition, basically about a year ago. So, and that's actually where we kind of got involved with this data. Now, if you look at the systems that work with this data set and the latest neural end-to-end dialog systems, a lot of them are based on the GPT-2 model, which is basically, it's like a huge neural network that is pre-trained on random texts downloaded from the internet. It can be basically anything. It's just trained to generate the next word. So you can basically give it this bit of text and have it generate this one. Then you give it this bit of text and have it generate this one. And so it's pre-trained like that, and that means that it's kind of, it's a language model. So it has very good notion of what is fluent and what words go with what other words. And this helps with like pre-training the system, so it's a very good starting point for training an end-to-end neural dialog system. And that's why a lot of different dialog systems, like all of these listed here, actually use that one. And I would say there's probably a few more. And now to kind of make it easy for this neural network that is trained originally to generate words, basically everything in the dialog, or everything that the dialog system needs to track, is represented as sequences of some kind of tokens. It's look like words, but there might be some special tokens, like I don't know, some end of something or start of something or this kind of stuff. But mostly there are generally regular words in all that. And the way this works is basically kind of a multiple passes through the network, or multiple steps of operation. And that is, first you basically feed the network with some kind of a context. So the history of the dialogue, basically what the user is saying or what the user was saying a couple of sentences ago. And you first decode the belief state. So you first decode the representation of the user preferences, you know, the area or price range of the restaurant, for example. And the second step is that you now take this belief state and you query the database, and you actually then feed this, some kind of representation of the results of the database. You feed it back to the network, and then you decode the response. So then you decode the actual system response. I'll actually show it in a bit more detail, but this is the basic principle of operation of all those systems. And this is kind of the state of the art, I would say, today in end-to-end neural dialogues. And so this is where we come in, or where basically mainly Jonas and Vojta came in and started building our own system based on this architecture. And it's basically the same general principle is actually based on one of those systems. And we have a few improvements coded into that. But I'll first show the general operation of our system, and then I'll point out what is improved, or what is kind of what led to some improvements that we observed. So as I said, first you basically have the dialogue context. So here you see that there can be multiple turns in the dialogue. So there's some saying hi, and then the user is actually starting to say something related to the task. But it can be basically any preceding dialogue context, and you just feed that to the GPT-2 language model, which is kind of fine-tuned or further trained for this task. And you first decode the belief state, or the information about the user preferences over the course of the dialogue. We're kind of skipping understanding single sentences. We want to understand the whole context. And what is decoded, or what this model is decoding, is basically this kind of representation. So you can see it basically looks like text. It's normal words. This word is no different from this word. This is like the same token for the network, which actually kind of helps. So we have a kind of a textual representation of the belief state, or of the user preferences. And now as the second step, where we take this and pass it through the database, which is like an external module, but the database tells us how many results we get. And we only use basically the number of results. And the representation, again, is just a piece of text to make it simple for the pre-trained language model, which basically only knows text. So we can just say that we have this many of matches for trains in this case. And now we basically take the context as well as the belief state and the database results, and do one more pass through the network to predict the actual response. And for the response, we actually use some sampling. So it's not always exactly the same. So I'm going to talk about it in a minute. And we generate delexicalized responses. And this is kind of standard in these kind of models, which means that you don't see you don't generate Cambridge, you generate destination enclosed in brackets. Or if you're talking about a Chinese restaurant, you don't generate Chinese, you generate food in brackets, and then some kind of post-processing step fills in that word. So this is the basic operation of that network and of the whole model. So you're getting from the context to the response via basically two passes through the language model. First to generate the belief state, and then to generate the response. And
so can I ask you for precision? This GPT-2, is it really trained in the standard way as you would train normally a language model, that means with everything? Or are you helping it a little bit by defining some categories, like for example numeral, so all the numerals would be replaced by some special keyword, all the geographical names by another one, or you really just pull
we just put in everything. There is like on the input there is basically no pre-processing happening. The only thing that we do as a help is when it's actually supposed to generate a response, it doesn't generate like the exact values of the slots. It just generates placeholders. So that's kind of I guess it's basically what you meant. Yes. That and in here, you know, it says there are over 1,000 trains, and this is kind of a special case. If it was just like 2 trains, then we would say like there are, and then you would have like a, oh sorry, it's too low, sorry. You would have like there are count trains, so you would have a placeholder for
okay, but the GPT-2 itself is basically just trained with everything. Like
yeah, exactly. Yeah, it's trained with everything. There is like no real tweaking of the vocabulary of the model. It's kind of still thinking that it's working with language.
Okay. Can I maybe just to make sure that
yeah, sure.
Make sure that I understand a bit. So you actually have in your training data these state belief, basically the belief state, so that somebody made the annotation that here somebody is asking what destination can reach, and this is what
exactly.
For that it should output, and then that is passed to the database to get something that is.
Yeah, I mean, you know, well, this is in the training data. There is this annotation, but the GPT-2 model is trained to predict it. So for like a new example, it will decode this bit in this kind of textual representation.
Sure, but then you take that state and that goes as a query to database.
Exactly. Yeah. And the database will just, you know, get like the number of outputs. For example, if you have like restaurants, we will not encode the names of the restaurants, because instead of actually producing the results with the names, we just put in a placeholder. So I don't know. You can say that, you know, we would have like a cannot write. Never mind. We can have like one match for restaurants, but and the database kind of knows which restaurant it is, right? And we know it. But the system only will, or the GPT-2 model will only see this bit, and will generate stuff like name is a nice restaurant or something like that. So it will generate a placeholder, and then, you know, some chunk of code can actually take the name of the restaurant from the database and fill it into into this, or like fill it for this placeholder. Does that make sense?
Sure. And there is one single GPT trained for both the...
Yes. That's a single GPT-2 model trained for both those tasks.
But it was pre-trained on tons of the data, right? And you just...
Yes, it was pre-trained for, or like it was trained for the tasks on data where the annotation is available. And it's during training, it's kind of oblivious of the fact that, you know, the database actually knows the names and everything. This is only for the operation. Sorry?
So in your training data, you already define this?
Yeah, in our training data, we have those placeholders, but we only have them on the output. So for the input, there is no change. There's like still Cambridge. If the user is asking for like a cheap Chinese restaurant in the city center, it's all in there in the exact words.
So we started with the QA session already. Just a quick question regarding the diversity of the response. I understand that when you have a Chacha dialog, then you want diverse responses. So
right.
But this is not a Chacha dialog, right? Here you are asking about some specific thing where I get from one place to another.
Right.
So why do you want diversity for response? Why do you want to use these?
Yeah, I mean, I know that this is a bit of a hot ground, I would say, because yes, you're completely right that you may not actually want the diversity. But then if you don't want the diversity, then why would you want to train a response generator in the first place? You could just train a model to predict an action, and then you could have templates filled in, and it would be probably much more efficient and much more reliable. But the thing is that if you talk to an actual human agent, for example, if you just called up a tourist information phone number and talk to that person will not repeat the same responses over and over, right? And so if you want to talk to this kind of system, it kind of gets a bit boring, and it discourages the user from talking to the system if it's always responding in the same way. So that's why we want to kind of have it a bit more varied. Obviously, we want it varied, but within the bounds of like reasonable language and actual true responses. So the hallucinations are a bit of a problem. So if you want more diversity, the network may actually make up stuff that isn't true. So it's kind of all within bounds, but we still want a bit more diversity, a bit more interesting replies. Because otherwise, this huge effort to train like a large neural model, you'd spend like 2 days of GPU time to train it, and then it will always respond in the same way. It's kind of a waste of resources, I would say. I mean, obviously, it's nice to prove a point, but if you want to actually get something more than you would have with the traditional architecture, then you probably want some diversity in the responses. Okay, right. So yeah, okay. One more.
One more question. Maybe I hope I'm heard at the mic. So why do you need those placeholders actually? Because it looks like that the GPT was actually aware that from the text destination is the thing that.
Yeah.
Why do you need it later when you generate the answer?
Well, I'd say the data is huge. There's like 10,000 dialogues, but it's still not enough to cover all the different, Cambridge would probably be fine, but it's not enough to cover all the various place names of Britain, or it's not enough to cover all the various restaurant names.
But I guess that the GPT only had to figure out that if destination equals Cambridge, then it's supposed to take this Cambridge and put it to the placeholder, which is
we're kind of slightly making it simpler for ourselves. You're right that it should be possible in principle, and actually I think that Jonas tried that. It worked, it just gave us lower scores. Which, obviously if you're competing in a challenge, then you want the higher scores. But you're right that in principle this is completely viable, and this is something we probably should do in the first place. If we want to have like a real end-to-end neural stuff, then this is a bit of cheating. I completely acknowledge that. So yeah, you're right. On the other hand, it's not just copying from this place, but it would be also copying from the database. So like the restaurant names, or I don't know, postcodes or phone numbers or this kind of stuff. So this might actually be relatively difficult for GPT even for GPT to actually learn to copy, for example, phone numbers correctly, because it might create, put in a number, but it might not actually be correct, which does happen if you do it. So yeah, we actually, Jonas, like my student, actually had like an extended version of that in his master thesis. But as far as I remember, it didn't reach like that level of scores, or like the success rate and this kind of stuff, as with using the placeholders, even though they are kind of cheating. On the other hand, everybody is doing that, and everybody is claiming they have a neural end-to-end system, even though they are using the placeholders. So that's our architecture. Oh yeah, one more point. we actually wanted the model to be consistent. So in addition to training it to generate word by word, we also train it to kind of detect whether what it generated is consistent, basically. And I'm going to discuss that actually in a bit more detail right now. It's kind of, yeah, an additional training task. So it's the model is not just trained to generate the outputs, and it's not just, you know, the base GPT-2 model. We actually added like one very simple layer on top of like the last word. After the last word is generated, there's one more classification layer that incurs additional loss, and this is added to generation loss. So if you take the, you know, basic setup where you have a GPT-2 generating words, you feed it with all this stuff, and I'm kind of skipping the database here, but you know, don't worry about it. It's just simplified. You just feed it with this, and you then generate like word by word generate this. So after you generate the final token at this place, you have like an additional binary classifier checking like, was this response consistent with this context and this dialog state? And obviously, in our training data, everything is consistent, or most of it is consistent. I kind of assume, but you want the system to actually train and to find when it is not being consistent. And that's why basically half of the data is artificially corrupted. So either the state or the target response actually gets replaced with something else that doesn't fit the context. So you have something like this. So instead of you know, having the system reacting to the user asking about the Italian restaurant, you can have a response that is actually not fitting the context. You know, the user says, I want an Italian restaurant. Response is, thanks, goodbye. And that doesn't fit. So the consistency classifier in this will say that this is wrong. This doesn't fit. And similar case, you know, the user says, I want a cheap Italian restaurant, and the state is saying something about a train to Cambridge, which doesn't fit. So that again is like a negative label for this classifier. So we add these like modified training examples into the training data, so that the system kind of learns to find when it's not being consistent, and this actually helps it to track the state and to maintain consistency. And I mean, this actually was already included in the previous system that ours is based on. And what we tried is, if you look at this inconsistent state, it just sampled randomly from the data from all the possible domains, and it's relatively easy for the model to train to kind of figure out that if the context is about restaurants and the state is about something else, such as trains, it's probably not consistent. So it's like a relatively easy task. So we made it harder for the system. And right now it's still about restaurants. It's just, you know, the system has to figure out that, you know, the user wants Italian, but the context or the state says Chinese, and this doesn't fit. So this is like a new version of the consistency tasks, which actually helps the performance. So it's basically making it harder for the system to distinguish when it's not making sense, and training it to distinguish when it's not making sense, which helps it actually make sense in like the real operation. So that's, yeah.
This auxiliary task, it has just one output, right?
That has one output, yeah.
Okay.
It's just, yeah, just a single
So
table.
it doesn't say if it is a bad state or bad response, it just says it is inconsistent.
Exactly, yeah. So all of these have the same label, just saying like not consistent. Yeah, I guess that might be a good idea to actually to train it to predict what is inconsistent. But we haven't tried that. Okay, so that's the consistency task. That's like one of the improvements that we tried to put over GPT-2 or over the previous models based on that. And there are actually a few more improvements that we did. And one of them is not really related to the model, it's just related to the data. So, we have just those 10,000 dialogues, and we actually basically made a lot more, or especially a lot more user inputs using back translation, which means that we basically took that data and then used machine translation to translate it to some other language. I mean, we used 10 different languages because in our department there is a machine translation system that is able to translate between English and 40 different languages. So we just tried them all, translated the data using all of them, then looked at a few examples and saw like which languages kind of work best, that they provide translations that are slightly different from the original. So, if you translate it like, to English, then let's say this is French, and then back to English, you don't want to get exactly the same words in exactly the same order, because you want a bit more diversity so that you have, different inputs to the model. And you don't want to kind of end up with some kind of a gibberish. So you still want the meaning to be preserved over these two translation steps there and back. So we just look at the data and chose the 10 languages that we thought worked the best. And then during the training, we train as normal, but instead of the user input, so instead of what you find in the data like this, we put in something that has been translated into a different language and then back. Oh, sorry. Now I have to find my place. Yep. It's this one. Yeah. So basically you have kind of like 10 times more data. It's the same dialogues, just with slightly different way of expressing the inputs. So that's one thing. Another thing is we actually looked at the data and we found that, and this is what happens with all data sets. If you're trying to collect a data set and you need a lot of annotation and the data set is large, you end up with inconsistencies. So we basically I think Jonas wrote just a few rules to check whether there are errors in the data that were easy to detect, and we basically just discarded like about 30% of the data and used just that for training. And even though it's just 70% of the data, it actually works better than training on all the data, because there's less noise in the data. So these things aren't some kind of fancy modeling approaches, but they actually work and actually improve the system performance. So these are basically ways to make the system a bit more robust, a bit more consistent. And we also included something to actually provide the output diversity. So there's actually two things. And that is the sampling, as I already mentioned, and then there is an additional loss, that basically training loss that penalizes the system whenever it generates repeated tokens, whenever it repeats stuff from the input. Obviously, it's weighted, it has a low weight, so the system is generally allowed to repeat input tokens. But if it can rephrase it and say it in a different way, it's basically promoted, or it's not penalized at all. So that's also something that helps us to get a bit more diverse outputs, a bit more interesting outputs. So these are kind of our improvements over like the base setup. And now let's have a look at how that works. If you look at, okay, never mind. If you look at evaluation over basically just the test data from the corpus, and you just generate one response, one turn using context from the data. Our system, if you compare, I mean, this is what is this? Yeah, this is inform rate, this is success rate, and this is blue score. But if you look at the numbers, it's kind of similar to everybody else. It's kind of, you know, nothing special. If you run through whole dialogues using a user simulator, it actually works better than what we could compare with. I mean, a lot of those systems are actually not even evaluated in the full dialogues. So if we compare to the one that was evaluated, I mean, in that those scores, it's kind of relatively close. And here you can actually see that the success rate is basically half of ours. So and you can also see that, you know, whenever you measure success rate over one turn, you know, just like looking at gold contexts and just generated in one turn and then feeding back in the gold reply from the data and using that as a context, it works much better than if you actually try a whole dialogue and evaluate it over whole dialogue. So, but our system kind of holds relatively well in that, and it held quite well even in the competition where it was evaluated by humans. So there were actually people hired over the internet to talk to our system with like a given task, what they need to look for. And here we actually fared pretty well. And if you look at the success rate, say, based on what the people reported, so they talk to the system, they get the replies, and then they're asked if they are happy with the replies. Then our system basically won the competition. If you just count that, the problem is that the replies often did not match the database. So even despite our consistency tasks and despite all the stuff that we did, our system sometimes just kind of makes up things and doesn't follow the database. So that's a main problem that kind of emerged from this human evaluation. So, you know, if you look at the simulator and this kind of stuff, there are things that you only find when you actually use real humans to talk to the system. And we actually confirmed that all of these, all of our improvements or all of our additions to the GPT-2 model are actually helpful, and we tried both the simulator and the corpus-based evaluation. So we confirmed that, but we found in the human evaluation that there are still problems, and that's why we actually tried talking to the system ourselves and record all the errors. Okay. Okay, sure.
If I'm reading it correctly, success, the higher the better.
Yes.
Like for all the systems in the table, it's actually better to just ignore the database.
Well, the problem is it's not like you cannot ignore the database or you shouldn't ignore the database. The difference is how you count the success. This is success basically reported by the users. And this is the success if you actually looked at whether the system actually provided what it should have provided.
Okay. The user was happy but with wrong answer. Because
exactly. The user was happy but with wrong answer because they did not know it's the wrong answer.
Can you maybe comment still on the results of the previous table, or just what the CPLs are?
Oh, okay, yeah. So this is basically complete rate, which means how often do you even get to actually providing some kind of entity. The success rate is, so you provide, for example, a restaurant. The success rate is you provide a restaurant, you're able to also provide everything that the user asked about it. For example, the user asks for a phone number and you actually provided the phone number. So that's that. This is, I think that just about the different slots. So it's like an F measure over slots that you're providing. And this is the book rate, which is if the user asked you to book a restaurant or to book a hotel, how often the booking actually was successful, or the booking was correct. So those are the evaluation metrics here. Okay, so that's the results, and yeah, basically based on what we found from the results, we actually decided to talk to the system and record all the errors. And basically, me and my 3 students did 130 dialogues, and we found basically errors in 50 of them, but only 17 dialogues were actually unsuccessful, where we didn't get what we wanted, because we were like highly motivated to try again if we found that the system doesn't make sense. So we mostly tried again. In most cases, we actually were able to kind of recover from a problem in the dialogue and get to what we were looking for. And we also found that there is that the system is actually able to handle a lot of things in like connecting getting the taxi from my hotel to this attraction, and it's working just fine. It's also surprisingly, and I say this is probably due to the GPT-2 model, it's surprisingly resistant to typos. So even though we typed and we only noticed later that we made some typos, it worked mostly just fine. And the errors we found kind of corresponds to what we saw in the human evaluation, and that is that in like the most common type of error is that the system kind of invents a slot in the user. Basically, I just say I'm looking for a hotel, and the system automatically starts offering hotels in the north of town, because it somehow assumes that I'm looking for a hotel in the north, even though I never said that. So that's kind of the most common problem that happens relatively often. In some cases, you get something like I found Chinese and Chinese restaurants or something like that. So basically just repeated values. That it's basically just not fluent. It doesn't matter too much. But in some cases, the system actually booked a restaurant without being asked to. So it looked like you would just say that you're looking for this kind of restaurant, and the system just straight away said, "Okay, booking was successful. This here's your reference number." So that's like not so great. In a few cases, we also get the system asking for the same thing repeatedly. So the system would ask you for the area. You would say, "Yes, I want the city center," and the system would ask for the area again. But in most cases, after like 2 or 3 tries, it actually picked up on that. So these are the kinds of errors that this kind of system makes. So it's by all means not perfect, but it's still, I would say, quite impressive what you can do with like the GPT-2 model.
The errors were eventually successful. So it could have been successful, but frustrating eventually.
Exactly. Yeah. So in most cases here, only like out of 130, like 17 dialogues where we kind of gave up and figured that it doesn't make any more sense to try and talk to the system. But in most cases, it was just one error, and in like the next turn, you ask again in a slightly different way, and it recovers.
Also, with those hallucinated values, did you look into whether it's the response generator that's over-eager, or did it somehow already mess up when writing down the belief state?
Right. Yeah, I think it in most cases actually was messed up when it was writing down the belief state. But I don't remember this exactly, but I can actually look that up in the paper later. I think we actually assigned each of those errors like the cause or the part of the generation process that caused it.
And the booking itself would be done eventually based on the belief state, not on the risk.
The booking was done, or is generally done based on the belief state, not the responses. So basically, when you query, well, I'm not sure. Yeah, here we go. When you query the database, in this case, you would actually also do the booking, and the database would basically tell you whether the booking was successful or not. So it's also kind of external to the system. But you need to enter the correct kind of parameters for the booking. You need to enter, you know, if you mess up the user preferences and there is no hotel to book and that with those parameters, then the booking will not be successful. Okay. Okay. Okay.
Regarding the retrieval from the database here.
Right.
How do you assess relevancy? Which match is more relevant than the...
Right. Okay, so if you have like, I mean, in general, you basically, like the database basically mainly return like the number of matches. So you know that there's like 3 relevant hotels, and the system or like the GPT-2 model doesn't even know when it's saying stuff like, I have three hotels. Do you want me to recommend one? And the user says yes, and the system says, okay, let's try the Golden Dragon. That's a nice hotel, or something like that. The system or the GPT-2 model doesn't even know which hotel it is recommending. That is basically just up to the rules that are kind of operating the database, and it's taken at random. So it basically just recommends one that is fulfilling all the user requests or all the user preferences. But if you have like 3 hotels that are in the city center, are whatever 4-star hotels, and have free internet or something like that, you just pick one at random, and the database kind of remembers what it picked, so that you can actually fill in the placeholder. But the GPT-2 model is basically completely oblivious of which one was selected. Okay, does that make sense? Yeah.
Those are deterministic queries.
It's basically I mean,
it is as long as
it
satisfies all the constraints.
Yeah, exactly. I mean, it's deterministic if you set the random seed. Otherwise, if it just picks randomly from the appropriate venues or appropriate places. Okay, so right. So basically, just to kind of conclude this, it works pretty well, especially if you actually evaluate over the whole dialogues and go beyond just looking at one turn. But it's still not perfect, and the main problem is the grounding, so actually being consistent with the database. And also it really needs a lot of data. The multiples data set is really large compared to others, and was probably quite expensive to collect. So that's kind of end of part 1, and I'm kind of running out of time, so I don't know if you're fine with me talking about the other experiments as well.
Absolutely. If there is anyone who wants to leave, we are free to leave, but I think
yeah, sure.
There's reason to keep Ondra longer than
So this is a slightly different experiment, but it's kind of follows from the last point. You need a lot of annotation, and it's expensive to get, and also it's domain or task specific. So the annotation you have for multi-walls doesn't really translate. If you have this tourist information system, if you had a dialogue system that would recommend you what movies you want to go to and book you a ticket, it will not work, because it's a completely different domain. It's a completely different topic. It has different types of slots. So different types of attributes. So for a movie, you would have a genre, you would have like user rating, you would have, I don't know, parental guidance ratings or this kind of stuff. And for restaurants, you have the price, you have the area. So it's really different and does not translate well across domains. But there is plenty of generic linguistic annotation tools that are automatic. So you have stuff like named entity recognition, or you have semantic role labeling or semantic parsers. I mean, you have other types of, you can probably think of other types of linguistic annotation that you have tools for, but these two are the ones that we tried in this experiment. And if you look at that, you know, if you look at the output of a semantic parser, there is stuff that is not so interesting. If you look at the named entities, and, you know, not all slots are actually named entities, so they will not be captured. So it kind of looks like this, you know. It's some bits of the dialog slots are captured in semantic parsing, some are captured by entity recognition, some may not be captured at all, but we kind of wanted to see how far we can get by basically just processing the generic annotation and trying to get relevant dialog slots. So the idea here is that we get some weak supervision from the generic linguistic annotation. Basically, you have some candidates. Then we somehow filter and refine those candidates. And then we try to apply them and try to actually use them in an end-to-end dialog system. So this is kind of like our idea, our setting for the experiment. Now let's look at how we did that. So the overall approach is that we start from some kind of data. We actually used some dialog data sets that had the annotation. We just removed the annotation and used it only to evaluate, to check how well we did. So we took just the text without any annotation and we applied some linguistic annotation tools, mostly frame semantic parsing, but also named entity recognition in one case. And for the frame semantic parsing, it's a good thing that there's basically hundreds of different labels. I'll show one example later, but there's many different labels, so that we can actually start from them and kind of join them to just select and select only the relevant ones. So you basically start from some kind of annotation, and then you try and figure out without any supervision. So this bit is kind of, it's unsupervised. You try to figure out which parts of the annotation are actually relevant for your domain. So if you're working with restaurants, which bits of the annotation, what parts of stuff that you get from the frame parser or the entity recognizer is actually relevant to your dialogue about restaurant. So this bit is kind of an iterative merging and selection, which I'm going to show in a bit. And you get some labels, some labeled data set out of the unlabeled one. And then using the labels, you can actually train a standalone slot tagger. So you don't even need the original parsers. You don't need to deploy them everywhere. You just train a tagger. It can actually improve over what you get from here. So because it can generalize better. So that's like the overall process. And I mean this bit is it's straightforward. You just get a parser or a tagger from the internet. You apply it, and you get some output. But the other two steps are a bit more interesting. So I'm going to show them in a bit more detail. So basically, when we're here in the merging and selection part, we kind of assume that we have some candidates for the different dialog slots from the annotation. And basically, we try to figure out, so we have stuff like, stuff like here, and we know that, I mean, this is labeled expensiveness or something like that from the annotation, and we know that this one is labeled location or something like, these. So we have labels like that, and we want to kind of figure out that this one doesn't help us because it's all about restaurants. This one is actually relevant. So that's the idea, and this is what we do here. So basically, we take for some slot candidate, which might be like this expensiveness. So we take all the words that are used in expensiveness, and we basically just average their fast text word embeddings, which are like pre-trained word embeddings, pre-trained representational words that you can just download. So we just average those for each of these slots, or each of these like slot candidates. And then if the candidates have like very high similarity of those embeddings, which is just cosine similarity, and also based on where they occur, so which verbs they occur with, basically. So we just merge those that are very similar. And there's just like a threshold that has been tuned, and if they're over that, we just merge. And then, so that's the merging. And then we just select the ones that are kind of relevant for our domain. So we basically, I mean, probably not that important to go into the process, but the idea is just that we have a few criteria based on which we rank the individual merged candidates, and we just discard the ones that are, not so interesting. So we just do this, and we basically repeat that. So if you discard something, you might actually find out that after the next step, something is actually still similar or still over the threshold, and you get another round of merging, then you get another round of selection. So you can repeat that until this kind of converges and doesn't do any more changes. So you can do it's normally this is just a few loops over this, like 2 or 3, not more. And this way we get the actual annotation. And for the annotation, we then train like a standard tagger, which is nothing special. We just used a simple LSTM sequence tagger, where the labels were either nothing or our merged slots, and we actually don't know the names for the slots, so it's not like price or area, because the annotation was slightly different and we merged something, and you don't know what label, so we just numbered them. And in practice, you would probably have to go and look at the resulting annotation and give it names to connect it to a database. But this is something we kind of left out of our experiments. But now that you train this tagger, you don't even need the original parsers, because you're not relying on them. You can just, you have a tagger trained on some kind of a labeled corpus, and it can tag new texts. So it's ready to use on any new data. And we also found in here that you have this label, like no label or no slot, and then you have some other slots. And if you kind of find a case where you know, the like no label is the most probable, but there is some candidate or some slot that you know, let's say slot 1 has a probability of like 0.25 or something like that. We actually have a rule that the tagger will pick that one as the output. So this kind of improves recall. It lowers precision, but very slightly. And we found that this works better in practice. So it's kind of able to generalize a bit more. So it is able to annotate even stuff that wasn't annotated in the first place. So if you look at this example where you have, this is the frame semantics. And this is the output of our tagger. So if you look at the, you know, user input, there is stuff that is not relevant or not so important, and this isn't tagged because this label was eliminated. This wasn't deemed important for our domain. But for example, here for this word, this is important because it's a type of cuisine. But the frames parser wasn't able to, or couldn't find this label, or I don't know why it didn't assign it here, but our tagger did. So here we found that we were actually able to do better than the original labels. So basically we have the like irrelevant stuff like this locale or the word food or this kind of stuff. This is removed. This is not in the annotation. And the meaningful stuff is kept. So stuff like expensive, cheap, that's kept. And sometimes the tagger actually is able to generalize beyond the original annotation. So obviously this is a nice cherry-picked example. It's definitely not perfect. So if you look at the results, and here I'm actually comparing, it's basically natural language understanding, and it's slot F1 on various different data sets. So you have restaurants, hotels, and flights in 2 versions. We even have more in the paper. And if you compare to stuff where you actually train a supervised model, you can actually see that, you know, our model comes relatively close. I mean, in this case, even, you know, similar to like a supervised dictionary-based method. And you can also see that if you don't use the tagger with this rule, you're typically doing worse. So you get some improvement from using the tagger. Obviously, it's in general worse than having the supervision and having the actual annotation, but it's better than previous unsupervised method, which is the one here in green. And you can also see that if you combine frames or the semantic frames and entity recognition, you can get better than if you just use the semantic frames. I mean, not by much, but, you know, slightly better. And what we also found is, yes, it's not perfect. You know, there's definitely some room for improvement. It's limited by the fact that some things are just not captured in the semantic frames or named entities. And the merging process is obviously also kind of not flawless. But it is some kind of annotation that may be meaningful, and this is what we wanted to try. So we tried to use it in an end-to-end system, and I must note that this actually predates our experiments with GPT-2. So we just used an LSTM-based system from those guys mentioned, but it's basically the same principle, just instead of a GPT-2, you have LSTMs. So it's the same, you encode the context, and then you decode the state, you know, then you go to the database, and then you encode everything, and you decode the response. So it's exactly the same principle of operation, it's just you don't use a huge pre-trained model, you just use recurrent neural nets with LSTM cells. So, and it also has kind of an unsupervised version where the state is decoded using some kind of a specific reconstruction loss where it tries to basically it has it has like a posterior distribution and it tries to match it over the decoder, but so you have like an unsupervised version where it's not using the state, or it's not using any state annotation, so we can actually relatively easily compare to that. And what we measured here, it's slightly different from the previous case, but we still have slot F1. The entity match rate is basically the success rate, more or less. And the goal accuracy is kind of exact match for state tracking over the whole dialog. But if you look at the comparison with like the supervised system where you have all the annotation, we're still not there. Like especially here, we're far from that. But if you compare to like using completely unsupervised model without any state annotation, I mean, this is a pretty huge difference from just using that. So if you don't have the annotation available, this is actually much better. And we can also see that we are doing better than just using the output of the semantic frame parser in the first place. So if you instead of using this weird, complicated process with the merging and selection, you just put in the labels from the frame semantic parsing, you can actually do better than unsupervised, but it's still not as good as what we are able to do. And this is especially true if you look at the actual success rate over the whole dialog, where we see that we found the correct entity. So and there's one more point. The label quality is important because here you actually see it for the slots, or for detecting the correct slots, you're actually losing by just using the semantic frames without any processing, without any refinement. So I'd say this was kind of a partial success. We definitely improved over the unsupervised methods. Obviously, we were not able to match the supervised things. But the thing is that you can find relevant dialog slots or the relevant attributes for your dialogues using processing of generic linguistic annotation. And the annotation is noisy, but can be still helpful. But we probably should look for some better sources of annotation than the frame semantic parsing and entity recognition. And we could potentially look into stuff like keyword extraction, which might actually work better than those labels. And so far, the annotation or all these things has been done on just like single sentences. So when we are looking for the relevant slots, we're not looking at dialog context, so that might also help. Right. So this was kind of the second experiment. I don't know if you want to ask something or.
So to the GPT-2, or in this case to the LSTM, how are you presenting the information? You just insert the word slot 0, slot 1 into the word string.
Yes.
And you prepend or postpend them after the given couple of words that you will be tagging, and that's just it?
Yeah, that's just it, basically. There's no special treatment, basically, of those things. For the LSTM, we have, I'd say that stuff like slot 1 or something like that is like a special token in the vocabulary, so we have a vocabulary entry for that. For GPT-2, we don't even bother with that. We just pass it through its own tokenizer, which is using subwords. So it can, it would probably break this up into 2 or 3 tokens or something like that, but we just leave it as is, and it works well enough. Okay, so I'll just, yeah, probably not go into details on that. I'll just mention a few problems with dialog evaluation that we found. And basically the problem here is that, you know, you have a lot of chasing of state-of-the-art, you have a lot of benchmarks, you have a lot of results tables, and you're trying to go beyond the models. And typically, if you look at the papers, you know, they just copy the numbers from the different paper, show their own numbers, show that their number is higher than in the other paper, and you know they are state of the art. It's done. The problem is that even on the same data set, so if you look at the multiples data set which I was talking about, there are many different implementations of the evaluation, and we found that they are really incompatible. And one problem is those slot placeholders, so different systems do it differently. One problem is database matching, and one problem is also blue score and its implementation, and basically how to determine if your dialog was successful. If, you know, like 4 different hotels match and your system found one of them, is it successful or not? You know, should it have found all 4 of them, or so how you compare, and these implementations all differ. So this is basically what we did. We compared the different placeholders for different types of systems. And if you see, these are like 5 different systems, including our own, and you can see that they're quite different. So, and this is actually annotation provided in like a newer version of the multiples data set, but these systems are basically from the same time as this version of the data, and they all use their own, and they differ quite a lot. And this is a bit of a problem because for all the comparisons, including the success rate, including blue score, this kind of matters. So what we basically found is that in blue score, just looking at the placeholders and different organizations, this kind of stuff, can make a difference of like plus or minus 2% blue score, which is a huge deal because a lot of the systems just differ in like 0.5 or something like that. So you get different ranks of systems. If you get, like, we tried 13 different systems, and you get different results tables based on who is doing the lexicalization or the like replacement with placeholders. And even for inform and success rate, all these things, based on how you count, you get vastly different results. And you know, you can typically see that the success rates reported in the papers are mostly higher than what you get when you compare, you do like one script to compare all these systems. I mean, some papers actually are hurting themselves, but mostly it's higher than like a realistic thing. And what we also found is that most of the systems actually don't care that much about diversity. So, for example, especially systems trained by reinforcement learning are using like maybe like 10 times smaller vocabulary than humans. So, I mean, there's many more results to this, but the point is that most systems are actually, as I said, kind of repetitive in their replies. I would say that in that case, you know, our system is actually doing quite well, but it still cannot match humans. So this 1/2 is basically our system, and one other that is kind of similar. So, and you can count other stuff to measure diversity, and it all doesn't look very good for the systems. So yeah, so basically that was the last experiment that I wanted to show. What I wanted to say is basically, if you take the pre-trained models such as GPT-2, it can work great, but it has problems with consistency. You can get around it, but only to a point, or at least we didn't figure out how to kind of remove this problem completely. And the same with the output diversity. I mean, if you just use GPT-2, it would be relatively bad. If you add the augmentation and the unlikelihood and sampling, it's better, but still not matching humans. Second part, it is possible to get relevant dialogue attributes from some generic annotation, but it needs to be somehow filtered, and you can actually improve end-to-end generation or end-to-end dialogue systems using this kind of annotation. And the last point is that, I mean, it kind of plugs into OGPT as well with our data operations where they help. So having clean data and, aiming at robustness is really important. It's as important as having a fancy neural model. And last point, it's really important to have standardized evaluation, because otherwise, yes, you will be on top of your results table, but it might not mean anything. So yeah, this is all I wanted to say. I hope it wasn't too long in the end, but if you have any questions right now, I'm happy to discuss.
First, I think we need to press.
Thanks.
No questions.
Yeah.
Right.
Just a quick about the evaluations.
Mm-hmm.
So you are saying that people were not using Zuckerberg or these telescopes.
None of those people were using Zuckerberg, which, just for context, is like the standardized implementation of BlueScore, which is basically 100% compatible with the original one, like from 20 years ago when it was defined. So yeah, none of those systems were using that. They were using their own internal tokenizers for computing BlueScore. Because the BlueScore is actually very well defined and relatively easy to implement, but the problem is that the underlying tokenization needs to be standardized, otherwise the scores may vary widely.
In your solution, you use this original.
Yeah, we use Zuckerblue.
Yeah.
Or Zuckerblue. I never know how to pronounce it actually. Right. Yeah, this is basically here.
So in the automatic slot discovery, so your model would produce two label slot as slot 0, slot 1, slot 2.
Yeah.
But the supervised model will have the actual slot names. Right?
Yes, the supervised model would have the actual slot names.
And how does the comparison happen there?
All right. Yeah. This is a bit of a problem. If you want to do the evaluation and measure the scores, you actually have to go and look at like a few examples for each of the slots and then assign the label from the original training data. So you have, you have stuff like slot 1, slot 2, whatever, slot 0, and then you have stuff like price, area, food, and then you have to basically go and do this thing yourself. To kind of connect them, but generally for like if you go for, I don't know, like this or this data set, it takes like 5 minutes to do this. So and it's only done for the evaluation. So we kind of don't consider that like manual supervision or anything like that, because it's generally not really needed for the operation of the system. But if you want to interpret the slots, you kind of need this. But then it's basically just 5 minutes of work to do this. So it's like, yeah, really simple. If you look into the paper, there's actually an example of like the input slots, or actually the merged slots from the frame semantic annotation and their mapping to the dialog slots.
And coming back to the first one.
Okay.
So you have translation to generate more training data.
Yes.
But since language models can generate text, did you actually try to generate training examples that are semantically similar to
Right.
examples?
Well, and yeah, simple answer, we didn't. But I am kind of wondering how you would try to do that. But I guess you could do that if you, I would say you probably would need to fine-tune GPT-2 to basically take one sentence as a prompt and then generate another sentence that is semantically similar. So if you took like semantically similar sentences from the training data and then you fine-tune GPT-2 to do that, then you could probably generate additional training data. So yeah, it could work. The good part about putting in MT into the equation is that you basically could even get expressions that are not even including in the training data. Whereas if you fine-tune GPT-2 to, based on your training data, it probably wouldn't, it would probably learn to be very similar to the training data. So it would be kind of rehashing the training data. This way you can kind of get slightly bit more variety. I'm not sure how much more, but I would guess it's a bit more.
So still for the second technique, basically I have the impression that you are taking these tags from the different taggers and name entity recognizers and so on, and then you are using something like clustering-based techniques.
Yes.
To somehow group
Yes.
them or merge them.
Yes, basically.
But I think that the metric is kind of cluster purity or this kind of stuff, and it's not really the end metric, which is the quality of your dialogues. So
True.
Would you be able to do that in this N2 and somehow like backpropagating the error towards this block?
I mean, that's actually a really great idea, and we didn't think of that. But I'm not sure how to do that actually, because this is
Me neither.
this is
Not even manager, so.
this is but it I mean, potentially somehow through, I don't know, reinforcement learning. I guess it would probably be very computationally intensive, because you would have to try and train the system every time you merge something. But yeah, it's definitely something to think about, and maybe we can actually figure it out. So yeah, thanks for this point. Okay, any other questions, comments, protests? Okay.
When you suggested that actually most of the errors are coming from GPT failing to correctly produce the belief state.
Right.
It kind of feels expected, because it has seen the whole internet to learn how to generate English, and now you want to produce something that's structured and probably quite specific. Did you do something like, I don't know, increasing learning rate for those tokens, or like putting more weight to the errors that backpropagated from the belief state?
Right.
Anything?
Yeah, not really, to be honest. The thing is, for example, the problem with like it learned English, and now it needs to produce a structured representation. It can actually pick up on that very, very fast. So you just give it like I don't know, like one epoch over the training data, and it will never generate something that is like invalid. So if you have the representation that I showed.
You say one epoch over training data, that actually means just your training data only. So that would be. So
yeah.
When you fine tune it, you already fine tune it.
Our training data. I don't mean the whole corpus on which GPT-2 was trained.
Your examples are always the complete thing, and you are trying to predict also. No.
Yeah, basically our training examples kind of look like this bit, where you have some context, and then you first try to, you use the example twice. You first use it to predict the state, then you use it to predict the response.
Transformer, what is it in GPT?
GPT, yeah, that's a transformer network. It's basically just a decoder. So it has and it has basically always the attention over everything to the left of the current token.
So basically, you are retraining it again even on those original sentences, which will be the questions.
Yes, exactly. Yeah, exactly. But yeah, if you have this representation, basically never, after one epoch, it would never, forget to generate this bracket or something like that, or it will always put in the equal sign. So the form of the stuff is basically what it learns first, and only then it kind of starts to pick up on the fact that if Italian is here, it probably should be also in here. So, but yeah, you're right. That this is kind of non-trivial task, and the model is not really like explicitly trained to do that apart from this consistency thing. So yeah, there's definitely like room for improvement here.
I was even thinking like, would it be way too bad this little bit? Like we would be going away maybe from the neural network that just predicts the next board, but something that would be maybe 2 levels, so that it would predict the board, but maybe also tell you which token I am, and then when it tries to predict, that it wouldn't try to predict food equals Italian, but food equals 1, 2, 3, 4, 5th board from the
Right.
context. So
I mean, there is, if you look at actually the one that we used in the second experiment, which is here, the LSTM based network. It actually has when you have the LSTM in the decoder, what it does is first predicts whether it wants to generate or whether it wants to copy. This is the so-called copy network. So there is like basically one binary prediction, and if it wants to generate, it predicts like a softmax over a vocabulary, and if it's copying, it looks at the attention model and takes whatever has the highest attention weight, and that copies that over to the output. So this is what the LSTM are doing. I haven't actually seen a copy mechanism used over GPT-2 or over the transformer architecture. I guess it's because it usually does it well, even without this, but I think it still might help. So yeah, it's definitely like a great point to use this to make it a bit more explicit that what you're doing is actually copying over the tokens. On the other hand, there are also cases where the user is saying something like, I don't want to spend too much money, and it means that they want something cheap, right? So in those cases, this wouldn't work. But yes, in most circumstances, it would probably improve slightly over what we have with the base model. Okay, yeah.
So you said the GPT would learn the structure after one epoch.
Yeah.
Would it be possible to take a model without any pre-training? Would it be quite
Without, you mean, yeah, I mean, this is kind of that, right? This LSTM is not pre-trained. And it, after a few epochs, it still like picks up on that. And obviously, the whole results here aren't comparable because the data here is just a single domain. It's just restaurants, nothing else. So it's much simpler, and it would probably be it probably wouldn't do that well on multi-walls, but it would still be definitely possible. So yes, you don't necessarily need the pre-training. It would learn all that, but it probably wouldn't learn it that well. I would say that, even though it's a different task, GPT-2 is a great initialization for your network. So going random instead of GPT-2 will probably hurt you a little bit. On the other hand, you can have a smaller model, for example, because GPT-2 is pretty large and it's kind of annoying to train. So you gain something as well. Okay.
Quick question. So you developed a GPT for a challenge.
Mm-hmm.
Right?
Yeah.
I recently read a paper about BlenderBot.
Right.
Which is a pre-trained transformer, pre-trained on Reddit conversations. So,
Yeah.
And they were claiming, I don't remember the dataset from the top of my head, but they were claiming basically thanks to this pre-training, blah, 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 it was working have you considered it in the challenge, or it wasn't existent back then, or?
Right. I mean, Blenderbot is an architecture that's like specifically trying to work in like non-task oriented systems, right? So it's mostly aimed at stuff like, hello, how are you? I don't know, do you have a pet? Do you like skiing? You know, this kind of questions, and you just chat to it in, you know, like a very general way. And it's not built to track the dialog state and you know, actually have an explicit representation of user preferences. I mean, it encodes the whole history, so it kind of learns about the user somehow, but it's not doing that explicitly. It's just the hidden state of the network that kind of contain this information. So I would say that Blenderbot would probably give you more variety, but even less consistency than our approach. Otherwise, I mean, I'm not sure like which of the pre-trained models Blenderbot is built on, but it's basically all pre-trained transformers fine-tuned to do something else. So it's kind of the underlying architecture is similar, but the training task is different. But I think it wasn't available when we started doing that. I'm not sure, but maybe if you took Blenderbot and then fine-tuned that, maybe you would get slightly better results. I'm not sure. It's just guessing. Right? You like take Blenderbot as an initialization instead of GPT-2 and try to retrain it for task-oriented dialogues. Maybe it would be better because you started with dialogues in the first place.
I think as we are turning slowly into L220 discussion, so I propose to
Okay.
officially
Sure. Yeah. I mean, I probably exhausted most of you. Sorry about that.
Even if it is not for the beer tonight. So thank you very much for your attention. Thanks Student Union for your help, and thanks Ondra for being here, and please stay with us a couple of more moments at our department just to discuss.
Thanks for having me, and I really enjoyed that. I hope you did as well.
Yeah.